minutes for questions. We'll send you a private chat message at 10 minutes and also at 12 minutes, just to help you keep track of time. And then if you're still going as we approach 15, I will come in and ask you to finish up. Are there any questions from our speakers before we get started?
Just to remind everybody, with this 12 minutes for the questions, I think it's fair to say that putting questions into the chat is the most efficient way to go. If we do have some extra time and if people want to speak up, you can raise your hand, but ideally it would be good to have questions in the chat.
I think we'll just wait one more minute and then get started.
Probably ought to get started now.
Okay. All right, let's get started. Hi, everyone. My name is Megan Kirk-Marion, and on behalf of the other conveners of this session, I'd like to welcome you to part 2 of the Extreme Precipitation, Past, Present, and Future. I just quickly want to start by acknowledging that I'm coming to you from Toronto, which is the traditional territory of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples. We have 6 great speakers lined up for today. We'll do 3, take a short break, and then do the remaining 3. And with that, I think we'll go ahead and get started with our first speaker. It's Yi-Ling Kuo from the University of Toronto. So go ahead and share your slides and take it away.
Okay. Okay, so hello everyone, I'm Yi-Ling Kuo from University of Toronto, and during this talk I will discuss our results on high resolution climatological simulations for South and Southeast Asia, and we particularly discuss the mean and extreme precipitation changes. So first, some introduction here. So the extreme concentration of population over South and Southeast Asia makes it critical to accurately understanding the global warming impact on South and Southeast Asia monsoon, while the complex orography over that region, including the Himalayas, the Tibetan Plateau, and some other local mountains like the Western Ghats Mountains along the west coast of India, makes it critical, makes the projection of monsoon intensity technically challenging. So here we analyzed a series of high-resolution simulations constructed using WRF model for South and Southeast Asia to dynamically downscale global simulations constructed using a CESM model to investigate the possible impact of global warming on South and Southeast Asia monsoon. Okay, so the main methodology we use here is the dynamical downscaling. So in this dynamical downscaling pipeline, we call it a pipeline. We have our global model runs first, and then the data are reprojected and pre-processed by the WPS before being used as boundary conditions for WRF. And since CSM has both ocean and atmosphere components, but WRF doesn't have an ocean component, we also incorporate a regional ocean model called CROCO through the OASIS coupler into WRF. CROCO is just another like a more advanced version of the ocean model ROMs. Okay, so as I said, we use WRF model to dynamical downscale or global models, and the spatial setup of the WRF for the study consists of 2 layers of domains, 30-kilometer outer domain, covering most of the Asian landmass, and 3 10-kilometer resolution inner domains, covering most of the Indian subcontinent, south of the Tibetan Plateau, and one covering mainland Southeast Asia. And there's a third one actually covering the Tibetan Plateau, but the result of this third one won't be discussed in today's talk. As I said, we also had a regional ocean model. So the white rectangle on the right on the figure here actually shows the ocean domain at 0.2 degree resolution, and our global model has a 1 degree resolution. Okay. So before we can safely use this pipeline to do any projections, we want to first validate our method. So here, this figure shows the distribution of average JJAS or summer total precipitation in a CRU observational data set, and in our CESM model, and in our WRF model. So in this figure, we can see that there is a predominant orographic forcing of the coastal mountains, and also there is a large scale gradient away from the west coast. And this results in very high precipitation rates along the windward side of the coastal mountains, and much less precipitation in the interior subcontinent. However, the representation of this orographic precipitation is strongly dependent on model resolution. The rain shadow over the interior of the subcontinent is like almost non-existent, or at least largely blurred in our global model, resulting in a very large overestimation in the rain shadow. And this underestimation is greatly improved in WRF at 10-kilometer resolution. So this gives us confidence in our method. So so we can proceed to do future projections. So we actually did projections for following the RCP 8.5 scenario for both mid and end 21st century. But due to time limit, I will only discuss the end 21st century results here. So this shows the precipitation changes in the average precipitation changes at end of the 21st century. So apparently both models, both global and regional models, project an overall increase in rainfall. However, the increasing trend is more uniformly distributed in the global model, and the local trends clearly vary from place to place in the high resolution regional model. And we also notice that the increase in precipitation over the southern region, over southern India, is smaller than that over the west coast and over the northern region. And however, the opposite trend has been observed over Southeast Asia. We have actually stronger, larger precipitation increase over the southern region. Okay, since the topic of this session is extreme precipitation extreme, so next I will discuss some results in terms of the changes in precipitation extremes. So for that purpose, we would like to use station data instead of the graded observational data. However, owing to a scarcity of observational records of sufficient length, it's actually difficult to detect changes in precipitation extremes, even with decadal return periods, let alone those with even longer return periods, which are expected to be significantly more extreme. So therefore, we want to aggregate observations from similar stations so as to increase the effective size of the record. And however, precipitation over the Indian subcontinent and over the Indochina Peninsula is characterized by large spatial variability. So the probability distribution parameters of the extreme precipitation must vary greatly, making it impossible to combine all stations. So here we apply a polling technique to combine data from different meteorological stations based on the similarity of their climate and seasonal cycle. So to do that, we first represent each station by a vector comprised of its climatological annual cycle of monthly mean precipitation. So we got 12 values per station basically, and then we apply the K-means clustering algorithm This K-means clustering is one of the simplest and popular unsupervised machine learning algorithms. It groups n-dimensional vectors based on their Euclidean distance into a priori determined number of clusters. And so for study, we 3 clusters were identified for each region. So we have one covering the north and central India, and one covering the southern India, and a third one covering all the stations along the west coast. And similarly for Southeast Asia, we also have 3 clusters, although we don't have that many stations as in South Asia. So again, one covering the northern region and one covering the southern Southeast Asia, and there are also a couple other stations that make up the third cluster. Okay, and this figure shows the seasonal cycle of annual mean precipitations for the 6 clusters we just defined. The left 3 for the South Asia and the right 3 for Southeast Asia. So in these figures, observational data are shown as black lines with error bars, and the downscale data from the outer and inner domains. So remember, we have an outer WRF domain at 30 kilometer resolution and inner domain 10 kilometer resolution. So those data are represented as solid dashed lines respectively, and the blue lines for the historical period, green lines for the mid-century period, and red lines for the end-century period. So in general, WRF reproduce, if you compare the black lines with the blue ones, in general, WRF reproduce the seasonal cycle of precipitation, while only the station cluster at the west coast of South Asia has a significant low bias. And it's also interesting to note that the southern India and the west coast of Southeast Asia actually has the largest total precipitation and the precipitation change in autumn rather than in summer, whereas both of these values are the largest in summer for the rest of the clusters. And all clusters are characterized by a significant increase in mean monsoon precipitation intensity. And these numbers on each figure shows their increase in seasonal precipitation during their peak precipitation season. So stages for most of the clusters, and in autumn for some of them, for southern India and the west coast of Southeast Asia. Sorry. Okay. So based on these clusters, we can then do extreme value analysis. So we did extreme value analysis based on the generalized extreme value distribution, so GEV distribution. The GEV distribution is a commonly used method for extreme value analysis, and is based upon the use of block maximal. And the block maximum basically means the largest values taken over a fixed number of independent and identically distributed random variables. The block size used in our study is 1 season. And so again, like in the previous figures, the black ones represent observational results, and blue ones for historical simulations, green, red for mid and 21st century projections. So if you compare the solid black lines and blue lines, we notice that the mean of the observational distribution is actually larger than that of the model distributions. We think this could be because the station observations are actually point values, but model output are in fact gray cell averages. So for comparison to observations and for the estimation of extremes, we employ a bias correction of the distribution mean and the temporal variation of the model output for each station cluster using the formula listed here. And in this formula, TBC and TRAW are raw and bias corrected model output, and O means observation, and this bar means temporal mean, and sigma means standard deviation. So after this bias correction, the distribution mean and the variance of the bias corrected time series are adjusted to conform to that of the observations in each station cluster. And the maximum likelihood estimation is then employed to decide the parameters for the GV distributions, and a single GV distribution is fit to each cluster. So, and then the bias corrected results are shown as dashed lines in all of these figures. So if you compare the red dashed lines with the blue dashed lines, so we notice that by the end of 21st century, there is an increase in the distribution mean of precipitation extremes, so represented by a rightward shift in the peak of those curves. And we also notice there is a flattening of the tail of the daily rainfall distribution in all clusters. And these numbers listed here represents the increase in the distribution means of extremes. So if so we actually find that the increase in the distribution means of extremes are smaller than that of the seasonal average rainfall over South Asia. So it's 30, 40, 20 here. But in the seasonal rainfall, it's 40, 45, 30s here. So meaning that that the maybe medians or small like intensity rainfall actually contribute more to the overall increase overall increase in rainfall. And however, the opposite trend has been observed over Southeast Asia. We have larger increase in the distribution means of streams than in the average rainfall. And also, the temperature increase is about 3 degrees over both of these regions. And that implies about a 7% per degree increase rate for the west coast of the west coast of India, and the northern and west coastal regions of Southeast Asia. However, this rate is larger than the closest Clapeyron reference value of 7% per degree for clusters 1 and 2, basically the majority of India, and for the southern region of Southeast India. And we actually explored a bit why that's the case. So we first think that by the end of 21st century, the warming at mid-troposphere over these regions are actually larger than surface warming. So if you actually use surface warming instead of like the warming at mid-troposphere, where most of the rain originates from, you would like naturally get a larger increase rate. And also by end 21st century, we are expected to see stronger monsoonal winds, and we also see larger moisture advection and the convergence over particularly over southern region of India, so which also contribute to that extra increase. Yeah, that's about it. So we used to summarize, we use WRF to dynamically downscale our global climate projections constructed using CSM, and we found that there is an increase in both average monsoon precipitations and also in daily extreme precipitations. And the Clausius-Clapeyron relation serves as a good predictor of extreme precipitation change over the west coast of South Asia and the northern and coastal regions for Southeast Asia. However, the extreme precipitation increases are projected to be larger than 7% per degree, the Clausius-Clapeyron rate in the majority of India and the southern region over Southeast Asia. Yeah, that's it.
Okay, thank you.
Did I go too fast?
If there are any questions, you could put them in the chat or raise your hand. We've got time for maybe 1 or 2 questions. So there's a question here from Alejandra DeLuca. I didn't understand how the bias correction was performed. Could you explain that, please?
Okay, sure.
Also, did the bias correction have any effect on future changes?
Okay. So first question, how bias correction is performed. So we have our raw time series model data, and we basically, follow this formula. We use the raw model output minus its average, and we also adjust the variance by, using this using the standard deviation of the observation over the standard deviation of the raw model output. So using this factor to adjust the variance, and using the average value of observations to adjust the temporal means of the temporal means of the time series of the model output. Does the bias correction have any effect on future changes? Yes, we apply the same method of, we use the same method of bias correction to correct all the future projections, so that they can be meaningfully compared to the historical realms, historical results. So this bias correction may affect the increase rate. This number is 30, 40, 20%, but the qualitative results, like the increase in distribution mean, and also the increase in extreme precipitation doesn't change with bias correction. As you can see that even those solid lines before bias correction, we can still see an increase in precipitation extremes.
Okay, Yuling, I think we need to move on because we're a little bit over time here. Thank you very much.
Sorry.
No worries.
Thank you so much. I think we'll move on to our second talk, which is Dominic Matt from Uranus. Go ahead and share your screen and start when you're ready, please.
Yeah, so you should hear me well and then see my screen, right?
Yes,
yeah, we're good.
Okay, perfect. So hi, my name is Dominic Matt. I'm currently working at Uranus in Montreal, but I was in the past year working at the University of Copenhagen with Jens Christensen, and also with the colleague at the Danish Met Office on the project called EUCP, so European Climate Prediction System, and this study took form within this project. So when I submitted the abstract for CMOS, the title was different. So the title has now changed to a cloudburst event in the changing climate on the challenge of getting amount, location, and timing right. So in this presentation, I'm going to talk an extreme event that hit Copenhagen in 2011. And this extreme event was a late afternoon cloudburst that completely flooded the city of Copenhagen, as it is well shown here by the amount of water that you see in the two pictures here that was taken in part of the city called Vesterbro. Something that you have to keep in mind when you look at those pictures is that Copenhagen is really flat. So all the water that you see there is coming from the cloudburst and not from some runoff from surrounding areas. So it was a really dramatic event. It was really close to being even more dramatic, since they were really close to have to evacuate the largest hospital of Denmark. Reason being that the electrical system in the backup one was really close to being submerged by this cloudburst. So it would have been really, really dramatic. So there was a lot of questions asked after the event by stakeholders, such as, was this due to climate change, and what should we expect for this event under warmer condition, for example? And this is the question that we tried to answer in this study. So just to give you an idea of what happened on that day. So synoptically, I'm going to be really brief on that. It was a warm front. So here, really a warm air, unstable, was coming from the Finland Bay. Here, what you see is a convective reflectivity movie from the radar in Denmark. So this is an indirect measure of the precipitation rate. You see here, this is, I think you see my arrow. I hope so. So this is, if not, tell me so. So this is south of Sweden here. You got Denmark right there, and then you got Copenhagen, where I'm showing with my arrow. So what you see there, something that strikes us when you look at this is that we are really building quickly. Systems are building quickly, and systems are really small and really, really intense. So there's no doubt, at least it was no doubt in my mind the first time that I saw that movie that was really a convective precipitation. And this convective precipitation was really, really localized and really intense, as it is shown here by the two figures. So to your left, what you see there, these are station-based observation for that day of that storm. And what you see over Denmark is, well, low to medium precipitation accumulation for that day. It's except at one point, which has reached the value of 135.4 millimeters. And this is at the Botanical Garden in Copenhagen city. So as you see here that this was really localized and really intense. The right figure here show you the intensity. So this is the 10-minute precipitation at the same station, so the Botanical Garden. And you see that most of the precipitation that fall in the Botanical Garden occur within 2 hours, with a maximum intensity of 64.8 millimeters. So that was a really, really intense and localized. We already know as modeler that predicting the precise location, timing, and intensity of such precipitation is really challenging. So there's no way we can use a deterministic approach to do that. What we have to do is to use a probabilistic approach, which translates for us as modeler to produce an ensemble of simulation. And this is what the guys at the Danish Met office are doing. Actually, they are doing this kind of setup since that event, because they have not done that before the event, before this really dramatic event. So first thing first, what the area you see to the panel A, this is the simulated domain. The domain of interest is shown by the black square, also panel B, and you see the red star is showing the Copenhagen city. For this setup, we're using the state-of-the-art forecast model, Harmony. Driving data is an ECMWF high resolution, a professional model, and the grid mesh is 2.5 kilometers. So to create the ensemble, they use something, it's called a scale time lag forecast. And this is what we use in our study too. So, and this is a quite clever way to produce an ensemble. So you first start with a control run that you start not too far away from the event itself, otherwise you're going to lose predictability, and then you let it run for some time, let's say 3 hours. And after 3 hours, you extract the difference. You take the difference between this control run and then the driving data set. And then you use this difference to perturb other member at the same initialized time that you started your control run. And then you redo the same thing sometime later. And if you do something like this, you will end up with a few members. In that case, in this study, you end up with 13 members, are quite really plausible weather trajectory for this event. So something that is not mentioned in that slide, it is quite important, is that we have a data assimilation cycle activated in the whole setup. And this is really important if you want to have something not right, but close to right, if you want to simulate that. So I'm going to jump to the result here. So this is the accumulated early precipitation at 4 o'clock, which is more or less where the peak of the simulated storm happened. So what you see in those 13 members here, you see something similar to what we have seen in the radar movie. Now is there's no doubt in our mind when we look at it that this is still convective precipitation. Now we see that small system, quite intense one. But you also see that all the members are depicted in a different location for those systems, and this is to be expected now with convective precipitation. I mean, this is due to the highly chaotic nature of this precipitation. However, this is really problematic or challenging for us if we want to, for example, foresee or diagnose the risk of high precipitation rate. Then how do you do that if they have a really different location? For example, if you take an ensemble mean approach like this, or you look at the ensemble mean, then you see that over Copenhagen, you got precipitation, so the location is right. But of course, the intensity is too weak because you average out all the really high intensity. So what you have to do is to take into account each of those members. For example, that member here has a bad location, but the intensity is reproducing what happened in reality, actually. So you have to take into account that there's a risk that this system could have hit Copenhagen. So by taking information from each of those members, we were able here to use something else, an ensemble mean approach, and to build what we call an index of the risk. For a threshold, for example, here's a threshold of 60 millimeters per hour. So I want to go into more detail about that, but I want to say about how we did this map, this index of risk. We did relax a little bit the spatial criteria and the threshold criteria. I think I can easily convince you that if you look at those figures to your left, where you see the most intense system, this is where you have the highest value of that risk to your right. So once we did that, we were able to reproduce then the evolution of that risk for the present day simulation ensemble. You see that the storm take form around 3 o'clock and then vanishing at the end of the day. And then at that point, we were able to try to answer the question from stakeholders, what is due to climate change and what would have happened for this event on the warmer condition. So what we did to answer that question is we did apply an adapted pseudo global warming approach. And here I'm carefully using the word adapted because you cannot blindly apply a PGW on such small scale events, because you might end up stabilizing the atmosphere, killing the convection, then having something totally different and concluding something for the really, really wrong reason. So what we did in our PGW setup is we make sure that we kept the vertical structure, kept the convection alive, and having something similar to what happened in the present day state, but by boosting up the temperature. So this is the first result from the colder ensemble, so 1 degree colder ensemble. So of course you see here that the risk is still there, and of course the risk is still there. The setup was made for that. But what you see is that the risk is indeed decreasing, and as you warm up the atmosphere, you see that the risk is not only increasing, but the storm duration is also increasing. And that was for when you selected the threshold of 60 millimeters per hour. Next question could be, well, what happened with other threshold, higher threshold, for example? And this is what this next slide will told you. And this is one of the main figure of a paper that we submitted some weeks ago that we hope that we're going to have a positive answer soon. But so how we build that? So to the y-axis, what you see here is threshold. So from 30 millimeters to 110 millimeters, and the x-axis is showing the evolution in time. And at each threshold, at each hour, we produce a map like this. And within the black square, and why within the black square? Because there were other risks over some lake over Sweden, and we didn't want that to influence our result. But we selected within the black square, we selected the highest value for each threshold in each hour. I just want to repeat that. For each threshold in each hour, we produce a map like this, and then we took the maximum value within the black square to reproduce that. So that was for the present day state. And then if I show you for the colder ensemble, then what you see here is that the risk is indeed decreasing, but you also see that there's some risk that was occurring in the present day state that was not occurring anymore. For example, the 80 millimeters per hour is not there when it was colder. And then if you warm up the atmosphere, you see some same conclusion that we have seen in the slide before. Now the risk is increasing, storm duration is increasing. But what you see also is that you got some risk appearing for threshold that was not existing in the previous ensemble, such as 100 millimeters per hour. And I think that was quite really a strong statement from this study or from this paper. So to conclude here, so this study was part, as I said, from a UCP, and it was from the task of storyline. And it was called an event-based storyline, where we started with one observed event with some question from stakeholders, and then we tried to shed light on that and see how the risk is evolving for this specific event, small-scale event. So just one last thing before ending. So the scientific question here, well, it was not what is the likelihood of occurrence, and what to expect for this type of event. But in the future, but rather giving this extreme event, what would happen if conditions were warmer or colder with a similar synaptic configuration? Thank you.
Okay, thank you. We have one question in the chat from Neil. I noticed that the storm system appeared to be propagating from the east. Did the large-scale flow play any role in this system?
Oh, yeah. Yes, it was. So I didn't show any map from the synoptic, but it was really a large synoptic scale. But it was initiated by really local condition. So that was tricky actually. So what happened in that day, it was, so you have the big system, and then the layer was really unstable, but convection was initiated by the convective temperature at the surface that reached the convective temperature. So the surface temperature reached the convective temperature. That's what initiated the convection, and that's what we see in there. So it was a mix of both, but synaptic driving forcing was important here.
Any other questions? Put them in the chat or raise your hand. Actually, I have one question relating to, in fact, your final slide. These warmings and the various risks associated with each degree of warming or cooling. One of the big modulators in precipitation is static stability, and I'm wondering to what extent static stability is modulated for each one of these conditions.
It is not. So what we use as a thinking in this study is that we really try to replicate if this really unique situation was occurring again in the future under warmer condition, what would happen. So we didn't take into account the stabilization. In fact, we took some time to produce this study, and the first setup that we did, we had stabilizing effect, but it was killing completely the system. So and the event was not there anymore. So the conclusion was, well, let's go for climate warming. I mean, this extreme disappear. So, and we realized that we killed it. We killed it, the event itself. It was not the same thing.
Indeed. Okay, thank you. I think we need to move on here. So our third speaker is Anna. Is that right, Megan?
Yes, it's Anna Urena from UK. So go ahead and share your screen and start when you're ready.
Okay. Are you seeing the screen?
Not yet.
Not yet? Sorry. Now?
Okay, yep, we've got it now.
Okay. Hello, everyone, and thank you for coming. Let me introduce myself. I'm Anna Urena from the UCAN University. I am currently working as a research assistant at the SCARE Center. And as you can see in the screen, the title of my presentation is Extreme Precipitation and their links with regional and local temperature, a case study over the Ottawa River Basin in Canada. As an introduction, I'd like to highlight how the possible changes in extreme precipitation associated with global warming have been the subject of numerous investigations. Higher concentration of greenhouse gases increase temperature, but also increase evaporation, which consequently enhance precipitation rates, storm intensity, and of course, the risk of flooding. In this context, the closest to a Bayesian relation has been widely used as a proxy of the evolution of the precipitation regime, including daily and subdaily extremes. According to this theory, extreme precipitation is expected to increase at the same rate as the water holding capacity of the atmosphere for temperature and pressure values near the surface. I'd also like to point out an interesting concept is the concept of hook shape, that this is explaining a sun increase in extreme precipitation at low temperature followed by a decrease at higher temperature. Saying that this study aims to verify the existence of links between extreme precipitation and air temperature for the Ottawa River Basin over the period 1981-2010. Here we use two variables, daily mean temperature and hourly and daily precipitation data from 3 simulations of the CM5 developed at the SCARE Center and the 5th generation of 2 reanalysis products from the ECMWF, ERA5 and ERA5 LAN. So this presentation will focus on the variation that can be observed in the CC relation. The first point I'll show you concerns the difference observed according to the temporal scale. Then I move on to the importance of the spatial resolution of the model. And after that, we will be looking at the hook shape behavior previously described. Here we use the methodology known as binning method. This method consists of creating temperature and precipitation pairs on wet days, grouping the data pairs in temperature bins, and then calculating the 99 percentile. To study the applicability of the CC equation, we use an exponential relationship which links the evolution of extreme precipitation and the temperature change, here alpha, also known as scaling factor, represents the rate of change of precipitation, and the value of 0.068 is the equivalent of the rate predicted by the CC relation. Let's now look at the first result. These graphics show the evolution of the 99th percentile of early and daily precipitation as a function of daily mean temperature. Here, all the green points were grouped by temperature beings of 2 degrees Celsius and represented as a cloud of points, and the solid line corresponds to the mean value. In general, precipitation increased up to 20 degrees Celsius, where there is an inflection point followed by a decrease or sometimes a stabilization of the 99th percentile. This hook shape is especially remarkable for early precipitation, as you can see in the blue lines. And less pronounced for the simulation lower resolution, it is almost absent for the reanalysis. Concerning the evolution of daily extreme precipitation, the model output also shows the hook shape behavior. However, this behavior was less pronounced than that for early extreme precipitation. Here in this second graph, the box plot was used to represent the scaling factor alpha for each grid point inside the study area. As you can see, alpha is close to the value of 6.8 for early extreme precipitation simulated at 0.11, with a clear tendency to decrease for course resolution of the model and also for the reanalysis. It can also be noticed that for several grid points at the higher resolution, the scaling factor is sometimes greater than the value of 6.8. This is also known as superclausus glabatum. Unlike early precipitation, as you can also see, the scaling factor alpha for daily extreme precipitation was consistently subclausus glabatum. That means lower than 6.8. These charts on this slide show the spatial distribution of the scaling factor alpha. For early precipitation, the difference between the scaling factor obtaining from the CM5 at 0.11 and the other data source was remarkable, especially in the area surrounding the Great Lakes where alpha was superclausus glabatum, which might suggest that the dependency between early extreme precipitation and temperature increased with the resolution. In the case of daily precipitation, the scaling factor was systematically subclausus glabatum and less than 5.5. Here in these charts, the white zones indicate the grid points where the p-value lower than 0.05 was not reached. This implies that there was no statistically close relationship between extreme precipitation and mean temperature in these areas. Same analyses were carried out in winter and summer season, and as you can see here, both extreme early and daily precipitation were more intense during the summer season. However, data shows that above temperature threshold of 20 degrees Celsius, extreme precipitation tends to decrease with temperature. So the objective of the last part of this study was to assess the link between atmospheric conditions at the synoptic scale and the decrease in extreme precipitation for the higher temperature observing during the summer season. To identify these links, 3 different situations were proposed. A, where temperature was lower than 15 degrees Celsius. B, with temperature between 15 degrees Celsius and 25, and situation C, with temperature higher than 25 degrees Celsius. Here, the colors on the charts indicate the geopotential high anomalies at 500 hectopascal. On the surface, solid lines indicate positive mean sea level pressure anomalies, while dot lines indicate negative mean sea level pressure anomalies. As you can see in the first case A, anomalies of the geopotential high at 500 are negative over the area. Here, the area is represented by a small yellow box. Here, which means this negative geopotential high anomalies means a mid-troposphere cooler than normal, and therefore a potential instability that can promote over motion and the condensation of water vapor. Here, the physical mechanisms favorable to the occurrence of precipitation seem more associated with well-defined synoptic scale systems, such as frontal zones. That was for the first case. The second case correspond to the average temperature values close to the seasonal climate normals in the study area. This situation is typically the synoptic and mesoscale condition found in summer in southern Quebec and correspond to the highest rainfall occurrence and intensities depending on the nature of the meteorological system affecting the region. For the third case, case C, unlike the previous ones, the hottest day showed a strong positive anomaly of the geopotential high, corresponding to a mid-troposphere warmer than normal. This positive anomaly can mean that anticyclonic synoptic situations cover the area, which are characterized by sunny days and therefore warmer temperature, which is often associated with low relative humidity. However, in these cases, precipitation events can be intense, but of course, less frequent. To summarize, the applicability of the CC scaling should not be generalized. In the study of extreme precipitation, other factors such as the time scale, the resolution of the model, and the season need to be taken into account. Also, that daily precipitation follows a lower rate of change than the CC scaling, while hourly precipitation increases faster with temperature. For the last part, regarding the hook shape, we can see that above the threshold of 20 degrees Celsius, the atmospheric moisture holding capacity was not the only determining factor for generating extreme precipitation, but it also maybe the moisture availability at the time of the precipitation event and the presence of dynamic mechanisms that can increase, for example, the upward vertical motion. So we strongly recommend to continue this line of research with very high spatial resolution simulation, such as convection permitting models and observed data, because this will allow us to better understand local temperature variations that play a major role in the occurrence and intensity of extreme precipitation. Thank you for your attention. Are there any questions?
Okay, thank you. Anybody who would like to ask a question, please do so in the chat. We still have time for questions. So Anna, I'd like to just inquire about the your 3-panel slide. It indicated the anomalously strong anticyclone with the warmer temperatures. I think there also, not only do we have with the mid-tropospheric warming and presumably less humidity, there probably is enhanced static stability, which also would be counteractive to enhancing the precipitation as well. Can you go back to your your screen?
Here?
I'm not able to see it.
Sorry. Sure. Okay.
I think the third, yeah, okay, so there's actually a considerable difference synoptically here, as far as I can tell, in terms of the geopotential height, the much higher geopotential heights in the warmer temperature column, correct?
Yeah.
So, I mean, the overall, I mean, the synoptic situation seems to have changed dramatically, so that the dynamical forcings here would be quite a bit more important even than the temperature increases, right?
Yeah.
I think that was one of your points.
Okay.
One further question here that we have from Amine. Have you also considered the availability of aerosols?
No, we didn't this study. No.
Okay. Are there any other questions? Yichen asks, for the current climate, the different temperatures are inevitably linked to different dynamics, large-scale flow pattern, which I presume would lead to deviation from CC, but would global warming lead to similar changes to dynamics? Yeah. The question is, would global warming lead to a similar type of dynamical structure that you're showing here?
For this study, we just use historical simulation, but there's been other study that say that, yeah, but in our case, we just use historical, the historical period. So.
Okay, well, thank you. So I think we'll have to close this part of the session. And just to try to remain on time, let's work towards coming back here in 5 minutes at 3:50 instead of the planned on 10-minute break. So we'll come back here at 3:50, but I would like to ask the third speaker in the next session, Farhan Aziz, to do a check on the presentation. Okay, so we'll see you in about 5 minutes. So Farhan, can you,
Hi.
hi there. Just want to do a quick check on your,
Can I share my screen?
yes, you can try that right now. Go for it.
Are you able to see my screen?
Yeah, it looks good. Yeah. Can you do a full screen? That looks good. Yeah.
Oh, that's great.
Okay, so we're good, Farhan.
Thank you. Thank you, Professor.
So Megan, are you there? You can stop screen sharing now, Farhan.
Okay, sure. Thank you.
No worries. So Chen, are you there?
Yes, I am.
Okay, that's fine. I think I probably ought to start out since it's 3:49 just by introducing you and me as the co-convener. So I'd like to give a preliminary welcome to the second part of Extreme Precipitation, Past, Present, Future, Part 2. So there's a Part 2 to Part 2 here. This is the second group of 3 speakers that we're going to start with. Megan and I are co-convening this particular afternoon session, and I would like to mention that my name is John Jackham, and my affiliation is McGill University, and McGill is situated on the traditional territory of the Kanien'kehá:ka, a place which has long served as a site of meeting and exchange among many First Nations, too many to mention here. So with that acknowledgement, I think we can start now with our very first speaker. And I gave myself the role of pronouncing everybody's name in this second part of this session. It's an easy job for me because Chen happens to be my PhD student, and I've tried to pronounce his name many times, most of them successfully. And Chen is here and he's from McGill University. He's going to give his talk on extreme precipitation regimes. So Chen, take it away.
Thank you, John. Oh, I need to share my screen. Okay. All right. So, hello, everybody. So today I'll be talking about synoptic scale environments and categorization related to winter extreme precipitation regimes, or EPRs, in Eastern North America. And this is part of my PhD work. As John said, this is my supervisor is Professor John Jackham here and at McGill University. And there's also been funding from FRQNT, NOAA, and INSERC. So to motivate, so as you will probably know, long-lived and widespread extreme precipitation periods often can lead to flooding, causing loss of life and property. So we see an example from Tropical Storm Imelda in Houston from a few years ago on the right. And forecasting such periods is still a significant challenge, and better understanding of these events would lead to better forecasting at longer lead times. And extreme precipitation studies have generally focused more on like individual storms or short duration periods, and not so much on the medium and longer timescales. So for this study, we want to expand the scope and analysis of these events by defining EPRs as periods of long duration periods of extreme and widespread precipitation, and to analyze the synoptic and thermodynamic environments during EPRs, as well as to categorize EPRs to hopefully obtain a stronger signal with lower variability within each category. So we used the ERA5 dataset for this for December to February of 1979 to 80 through 2019 to 20, and focusing on Eastern North America, which is pretty much this brown shaded region here, encompassing the southeastern, the eastern U.S. as well as the most heavily populated area of southeastern Canada. So here, to identify an EPR, we first calculate the normalized precipitation at each grid point. So that's the daily precipitation divided by the 80th percentile. So we have an example on the bottom right. We have the daily precipitation for a particular day. And then we have the 80th percentile, and this is for all winter measurable precipitation amounts. And we see that this is much higher to the south and to the north because we have the proximity to the warm, moist Gulf of Mexico and Western Atlantic. And so the normalized precipitation would kind of weight areas to the north a little bit more than areas to the south for the same amount of precipitation. And this kind of this has an effect of when we're calculating the precipitation volume, which is just the areal sum of this normalized precipitation over all these grid points, that will hopefully tend to prevent this the volume from being contributed just from like the heavy convective events isolated in the southern or the deep south the United States. So and we could define extreme to be at least the 70th percentile, again, of winter, of this normalized precipitation, which may not seem very high, but we do also need it to persist for at least 5 consecutive days, except allowing for 1-day breaks if at least 2/3 of the days meet the extreme threshold. We also categorize EPRs based on the spatial anomaly correlation, or AC, of synoptic scale weather patterns. So basically what this equation is doing is that if we have, say, we can have taking the we have like a spatial anomaly pattern of a certain field if you have a composite anomaly field, and then we take each EPR individually, how similar is that of that individual EPR's anomaly field, how well does it correlate spatially to the composite? So that's kind of what this is calculating. So there'll be one value for each EPR, -1 will be perfect anti-correlation, and +1 would be perfect correlation. And so here we're using the sea level pressure, or SLP, as well as the 1,000 to 500 hectopascal thickness ACs to define high AC EPRs as basically we need both of them to be at least 2/3, and the top 2/3 of our EPRs. And so we look at this plot here, we find the 2/3 thresholds in the dashed red lines here and here. And basically everything in the top right in this black box here is indicates the high AC EPRs. And so we kind of see they're more clustered. These values are more clustered up here, and then the low AC EPRs are kind of more variable in a sense in these values. And we find 62 EPRs total, with 29 being low AC and 33 being high AC. So pretty much a half and half split. So now for some composite results, so this is not doing any categorization yet, this is just overall EPRs. We find that first we're looking at the 500 hectopascal pattern. So shading is the high anomalies, and we find at the start of the regime a trough in the western US, a ridge in the eastern US, and then by the middle of the regime down here, it's kind of similar but shifted slightly to the east, and then by the end, it's really shifted well off to the east and kind of weakened a bit, or at least less consistent. As far as on the middle column, we have a low level equivalent potential temperature, or theta E in shading, or the theta E anomalies, I should say, and SLP in the blue contours. So we see kind of at the start of the regime, we have a high pressure just off surface, high pressure just offshore, with warm and moist anomalies and broad southerly flow into this region off the Gulf of Mexico. By the middle of the regime, it's still a lot of warm and moist anomalies, but slightly expanded eastward, and then kind of pushing eastward off the coast by the end of the regime. As far as the precipitation rate is concerned, we see at the start, the precipitation focused mostly in the western part of the domain, but kind of spreading eastward by the middle of the regime, and then by the end, it's kind of mostly confined to near the East Coast region. We also look at the moisture budget. Using this equation, and when I'm calling the moisture flux here, or at least the total moisture flux is basically this term here. So this is basically measuring, go back up here, is measuring how much of integrated vapor transport is fluxing through this boundary here. And we actually separate it out also into like a northern, western, and Gulf of Mexico and East Coast boundary like that. And so we look at this plot here, the black line is the total moisture flux, and that is the peaks at the start of the EPR, and then the precipitation lags just behind it. So we see a pretty good, that we need this moisture flux kind of contributes to all this precipitation, and both kind of fall off towards the end of the EPR. And most of the increased flux comes from the Gulf of Mexico, showing the cyan line in here. So we find a very, very similar pattern to the total flux. We also look at a few high split backward trajectories. Here, this is actually the NAR, not the ERA5, because high split doesn't take ERA5, but still should be a decently good data set. And we have here we're looking at 3-day backward trajectories with one trajectory every day of these EPRs, these 4 example EPRs. And so these are all ending at the black star here and at 1,500 meters above the ground level. Oops. We have a lot of these many trajectories coming in from either the southern US or even also coming off the Gulf of Mexico, Western Atlantic here. And many of these tend to also be rising on their way, producing clouds of precipitation. We also see many trajectories also from the west and northwest from much drier locations, and these tend to occur during breaks in the precipitation. So it's not like, at least at the black star, so it's not like all locations are constantly raining all the time or precipitating. So now we can compare low and high AC EPRs, and we see that here we're looking at the mid time of the middle of the EPR, but this is kind of similar for the other times as well. And we have a stronger fine hectopascal ridge and trough pattern in a high AC EPRs compared to low AC EPRs. And then we also have lower standard deviations indicating lower EPR to EPR variability in the synoptic scale patterns during these high AC EPRs. We also find that high AC EPRs tend to feature slightly bigger moisture fluxes, and especially from at least the total moisture flux, especially from the Gulf of, and especially also the one from the Gulf of Mexico. And this is the same plot as before. So we kind of see the cyan line here is bigger than in here. Finally, we also have high AC EPRs also tend to feature slightly less precipitation near the coastline, but somewhat greater precipitation inland compared to low AC EPRs. To summarize, we find that EPRs during the Eastern North American winter are characterized by a trough in Western North America and a ridge in Eastern North America at 500 hectopascals. And this pattern slowly moves eastward throughout the EPR. And this favors a transport of southerly flow of moist tropical air from the Gulf of Mexico into Eastern North America. And so we kind of see that kind of the schematic of kind of a generalization of what we tend to see during EPRs. And this also fits, or at least consistent with other studies done on at least shorter duration precipitation events in different parts of North America. High AC EPRs have stronger and less variable 500 hectopascal features on the synoptic scale, with greater moisture flux from the Gulf of Mexico, as well as somewhat heavier inland precipitation, but less precipitation near the coastline compared to low AC EPRs. And so that's it, and thanks for listening, and I'll take questions now.
Great, thank you very much. Just a reminder to put all of the questions you have for our speakers into the chat. So I will start with the first question we received. What event durations did you examine in the EPR analysis? Was there any relationship between the impacts and the duration of these EPR?
So I mentioned that there was there's a 5-day minimum. It turns out that the longest one from this methodology is 13 days. Most of them are kind of more like in the 5 to 7 or 8 day range. And I didn't really look at, I didn't really look too much at the relationship between like the impact and the durations, but I did find like there are quite a few, like for example, like the 2018, there's one event that's, in fact, part of that, the example that I show like on February 20th, 2018 for the example I show for the precipitation normalization example, that one actually led to a lot of flooding across the Mississippi, like in the Ohio and Mississippi valleys. That was about the 7-day regime. And so and certainly there was other ones like the 1995 event. Also, like there's also the ice storm in the big ice storm in Ontario and Quebec was also an EPR that lasted 6 days. So it's not clear. It's not necessarily clear if the length of the EPR correlates with the extent of the damage, but it's kind of, or impacts. But certainly, like when you have like 5 or 6 days or longer, there can be significant effects.
Thanks. We have one more question, I think we have time for. Can you comment about the seasonality of the events that are selected? Do they occur mostly in summer?
So actually, I've actually only looked at winter events so far. So I've not, and all of the percentiles and like the methodology was all done for winter only, so December through February. So I did not look at summer at all for this. I mean, like summertime will likely be more driven by like convective kind of events. Here there's still convection in like say the southern US, but like a lot of these events tend to be more characterized by like synoptic, several different like synoptic scale systems moving through. So it's probably I don't think I could really generalize to what happens during summer.
Okay, thank you, Yi-Chen. I think we should move on at this point.
Yep, thanks.
The next speaker is another person whose name I have pronounced many times in the past as well. And the speaker's name is Julie Theriot, who's from University du Québec à Montréal, just a few blocks away from McGill University. So Julie, thank you for coming today, and let's start.
Okay, great. Can you hear me okay?
Yes.
Okay. Okay, super. Thank you very much. So good afternoon, everyone. So today I will give an overview of a field campaign that we've done last year, which is called the St. John River Experiment on Cold Season Storms. The acronym is SAGES. So we found a name in English and an acronym in French because the experiment was in a French-speaking region of New Brunswick. So I would like to acknowledge my co-authors and those who contributed to the project that are listed here from multiple universities, Environment Canada, and this project was funded by Global Water Futures. So before starting, I will just show you where it is exactly, where was the field campaign was. It was in the Edmundston area, located in northwest New Brunswick, here on the border of Maine, US, and Quebec. And so it was like here, Eastern Canada. And we chose this region because in this region, the St. John River experienced multiple extreme flooding events since 2008. And it's the rapid snow melt in northern part of the St. John River that the water flow in the river and caused those extreme floods in the Fredericton area. Also in this area, there's often ice jams over the river and can cause also local flooding. So the occurrence measurements of precipitation, including snow and the phase of the precipitation, is critical in this area. So the objective of SAGES is to investigate the processes associated with the temporal and the spatial variability of precipitation amounts and phase during the cold season storms over the upper St. John River Basin. So to do that, we organized a field experiment during the winter 2020 and 2021. And this include an intensive observational period during the March and April 2021. So we chose this time of the year because, as you can see here on the climatology, so you have precipitation amount and temperature, and these are the month of the year. So around March and April, it's the month where it starts to have less snow falling and more rain, and it's also the time of the year where the temperature is near zero. So the objective of my presentation today is to present to you some of the data that was collected and also discuss some preliminary analysis. So first, the experimental design. So it was basically done with three main components. So we had first a long-term observation fixed station located in Edmundston. So here on the map. So the instruments were operational for from December to April. And then for the intensive observational period, and to be able to do manual observations, we deployed a mobile weather station for the month of March and April, almost at the same location, but it was closer to the St. John River. And then to be able to characterize the spatial amount of snow and also try to diagnose then the phase of the precipitation, we enhance the COCORAS number of observations. So they're usually around 1 or 2 observers. And for SAGES, there was up to 20 stations. So we have enhanced this the network for this for that winter. And we also use technology that is developed in Italy at the company called Artist. It's called a smart rainfall system that uses the attenuation from satellite signal using TV parabolic dish to estimate the precipitation. So if I go in a bit more detail with showing you some pictures. So our fixed station that was installed throughout the season, the cold season, we had sensors to measure a hot plate to measure the amount of precipitation, the characteristic of precipitation using a distrometer, also a weather station. And to characterize the precipitation aloft, we have a micro-rain radar. And we were very lucky to be able to install our instruments at the same station as the ECCC and Winston Weather Station. So you can see on this picture, the ECCC station, and far away here, we can see our station. So for March and April, we have installed the flux measurements of water vapor and also some sensors for soil and temperature in the ground. So for the observational the IOP, which was in March and April 2021, some manual observations were made, and also we enhanced the meteorological measurements by adding an extra micro-rain radar and weather station. So at the trailer, we were also able to prepare and launch balloons. So we launched up to 40 balloons during SAGES. And we were also very lucky to be able to borrow the Meteo Swiss multi-angle snowflake camera. So where it takes high definition photos in 3D of particles falling through it. So you can see here some examples of photos that were collected. And then another important component of the project was the contributions from the community, where we enhanced the COCORAS network. So there was up to 20 stations, and we had up to 70, 80 volunteers, because some full class of 6th graders contributed to the project. And then also the parabolic dish. And here, this is an example of the distribution of the total amount of precipitation during the month of March and April. So to give you an idea of what was collected during SAGES, this is an overview of the precipitation events, amount, and phase. And the top panel is the temperature, and the bottom panel is the amount of precipitation in liquid water equivalent, and the time here since December 1st. So we can see in red the 2-meter temperature, and in blue the dew point temperature. So we can see the variation of temperature. It was a relatively warmer winter in 2020-2021, and a bit drier as well. And we can see the occurrence of near zero conditions, and almost half of the time that it was near zero, there was some precipitation. But we can also see like mixed precipitation in December, mainly snow throughout the winter, and during the IOP, it was a mixture of precipitation, and here this is a big slush event. It was quite an interesting event here. So mainly snow during the cold season, and the occurrence of rain and mixed precipitation increased a lot at the end of March and beginning of April. And also one thing we were doing at the same time is we're trying to document also the evolution of the ice on the river. So we have pictures that the river was covered of ice on March 19, and the ice broke up in the northern part of the river near Edmundston at around March 26th, and it was free of ice a couple of days after. And this all happened during multiple events, so a chain of events that were before the ice breakup on the river and just after the ice breakup of the river. So on this plot, we have the precipitation here showed by the bars and the temperature and dew point. We can see also that during that week, the temperature was really close to zero. And also we see a change from rain to snow, snow mixed with ice pellets, so all kinds of precipitation at that time. And the ice started to break up on the river after a long rain episode. And then I should mention, this is really important, that it was quite difficult to be able to anticipate and know which phase of the precipitation would be because the temperature was so close to zero. And here I'm not showing any in the presentation, but when we were launching soundings, the temperature was also really close to zero aloft. So this is an example, again, of the data that was collected at the fixed station. So that was during the event where the ice broke on the river. And then we see the precipitation amount and the type also in color, and then the evolution of the temperature. So during this event, 22 millimeter of precipitation accumulated. So if I go back here in the time series, this is this event in particular. So this event, rain followed by snow. And then for the rest of the week, what the emergency measures were watching, for example, is the amount of precipitation that would fall and then the phase of the precipitation, because then that would impact the water level. And then you can see on the microrain radar different patterns of the precipitation aloft. So you can see the reflectivity increasing near the surface when it's rain at the surface. And here you have a mixture of snow pellets and snow at the latter part of the event. So we see this transition of precipitation. And from the optical distometer, we can see the fall speed and diameter of the particles, precipitation particles falling. So this is following the rain theoretical fall speed, and this is the snow theoretical fall speed. And then you can see a lot of instances where there was a mixed precipitation. And we can see also that particles reach up to 8 millimeter diameter during the event. So during solid precipitation events, the type of ice crystals were documented. This is a count from the microphotography that we're taking during SAGES. And so we see a lot of different types of ice particles. We see that ice pellets and irregular were also very common on the photographs. And then we see, for example, on March 29, these looks like a partially melted snow that refroze, and then you can see these spherical ice pellets, which is really interesting. So those type of particles may come from different locations aloft and were transported differently, probably by the wind. And on the 27th of March, you can see those bullet rosette. And interestingly, also during SAGES, there was often freezing rain on the forecast. We were always ready, waiting for freezing rain, but nothing happened. So when freezing rain was on the forecast, it was mainly ice pellets, and the temperature again was really close to zero, so too cold to be freezing rain. So the outcome of the project, so this is very preliminary. We're just working now on the analysis of the data, but we noticed that the amount and the phase of precipitation varied across Northwest New Brunswick from storm to storm and during storms. That year was relatively dry compared to the climatology. The mixed precipitation events occurred throughout the year, but was mainly common towards the end of March and early April, with this very interesting slush events on April 20th. When the ice broke on the river, it was during a chain of events of precipitation. So first, the rain probably help with this ice broke up on the river, and then after we're watching the phase of the precipitation and the intensity that could impact the water level. Another important aspect of SAGES, where we worked a lot with the community. That was during COVID, so we needed help from the community. New Brunswick was closed, and we had to work closely with them. We worked also with the regional weather forecasters and local government when we shared our soundings, weather information. And so the way that, for example, some partners noticed that we're there, noticed the number of stations of Kokoras in the area. And so that was very helpful for them with those daily measurements. And with the community involvement, when you have stations across the region, we're able to better quantify the spatial distribution of precipitation amount and phase. And sometimes we can see some like rain on the one side of the region, more east, and the snow on the other side of the region. So SAGES overall will contribute to improve our understanding in the atmospheric conditions and the precipitation processes when the temperature is near zero and during the cold season, and those can lead to a extreme flooding event along the St. John River. So now we have a few ongoing and future projects that are about looking at the impact of the precipitation phase on the evolution of the snowpack. Some analysis of mixed phase particles that could have been photographed by the mask, and also looking in more detail in the atmospheric conditions and the precipitation around the ice breakup on the river, and also comparing those conditions during SAGES with the conditions that led to the extreme flooding events in the past years. Thank you very much for your attention, and to all the participants to the project as well.
Thank you very much. I think we could probably squeeze in one quick question, and there is, oh, here we go. Did the project include measurements of snow water equivalent by the Kokoras and NB rover station?
Yeah, so the project, for the Kokoras observers, they were collecting the precipitation and the gauge and melting it, and also they were collecting the precipitation on the whiteboard for snow depth, and as well every Monday there was a measurement of the SWE of the snowpack that was done as well. So all the data is available on the Kokoras website.
Great, thank you. I think we'll move on to the next speaker, but there is one more question in the chat if you'd like to answer the question in the chat.
Sure, thank you.
Okay, so the final speaker in this session is Farhan Aziz from the University of Prince Edward Island.
Hello, everyone.
Good, good.
Yeah, my name is Farhan Aziz, and I'm a PhD student at the School of Climate Change and Adaptation, University of Prince Edward Island in Charlottetown. Are you able to see my screen?
Yes.
Okay, yeah, so let's start. Yeah, today I will talk about wastewater flooding risk for the city of Charlottetown here in Prince Edward Island. So Dr. Xander Wang, my supervisor, is also partner of in this project, and this project is part of my PhD. So let me introduce the study. The current study actually based on the assessment of the capacity and resilience of existing wastewater collection system in the city of Charlottetown for current 2020 and future 2040 scenarios, coupling with population and extraneous flows resulting from sea level rise and rainfall events. The study area, the city of Charlottetown, is a coastal city, experiencing the impacts of climate change in the form of sea level rise, and there's a population growth in recent years. From 2016 to 20, around 10,000 inhabitants are increased in the form of new immigrants and other people moved from other areas of PEI. So over this period, actually wastewater system is not increased with the same proportion. And during the recent extreme rain events, there are many basements were flooded due to sewer backups, and also there are some untreated water was on the streets. So to keep in all this in mind, we decided to study this. During the recent September 2020 rainfall event, which is almost equivalent to the 100 years return period. So if you see at the bottom of this slide, the average daily sanitary flows at the inlet of wastewater treatment plant are around 140 liter per second. But during this wet weather event, we received 652 liter per second, which is 4 times higher than the average daily flows. So these extra flows are actually creating a risk of flooding to basements and low-lying areas in the city. And also they are mostly increasing O&M costs to both treatment and collection systems. So this is the main purpose of studying this case. So the main objectives are to develop a detailed existing wastewater system model using PC-SWIM modeling framework. And the second objective was to assess the capacity of existing wastewater system for both current 2020 and future 2040 scenarios by applying coupling effects of sea level rise, population surge, and network age, and other things. And also to map wastewater flooding or sanitary sewer overflows for areas in the city for both future and current scenarios. So this is the existing system of City of Charlottetown, which is comprises of 34 lift stations, around 253 kilometers of gravity network, and 21 kilometers of force mains, and an existing treatment plant. So according to the current wastewater system analysis, 45% of the city's wastewater collection system is more than 25 years old, and 25% is more than 50 years old. So due to this age of network, there are a lot of blockages, and there are a lot of issues with capacity, so which needs to be addressed. So here on this slide, I'm trying to present the network age analysis. So if you see around 9% of our network is more than 100 years old. So we have particularly problems in those areas. So the most of the material of these pipes are concrete, which has more average age than other materials. So here on this slide, we'll discuss about methodology, model built up, and the flows. Model was built in PC-SWIM, developed by CHI Canada, and we used EPA SWIM engine inside PC-SWIM with many empirical method to assess the capacity of existing system. 15% extraneous or base flows were applied to the current 2020 scenario, and 20% are applied to future 2040 scenarios. These are calculated based on SCADA data analysis of flows received at the inlet of wastewater treatment plant particularly during the wet weather events. Meaning roughness values from 0.013 to 0.02 were applied based on the age of network. So these are classified for 50 years. We applied different values for network with age between 25 and 50. We applied different values, and so on. So if you see, the flows are proportionally increasing from 2016 to 2040. And next is the results of 2020 scenario. All these red dots or lines are showing flooding areas. And if you see, most of areas are in downtown near to sea. This is the most aged network in the city. So after discussing with authorities and sewer and water utility department, a cutoff value of 80% is applied. Where there is a pipe depth or you can say capacity is more than 80%, this is considered as flooding. So it is around 10% of the total network in 2020. But if you see on next slide in 2040, it is more than doubled or around double due to increased base flows from wet weather events and increased population and age of network in 2040. So we have more than 20% area is flooded. You can see all these red lines. These network or pipes are flooded with this population and other parameters. At the end, we recommend the city to upgrade the aging wastewater network at locations where structural deterioration has already been started in the form of retrofitting, and then we can improve the city's coverage for existing stormwater system, because due to less coverage of existing stormwater in the city, the rainwater mostly entered into wastewater system through the manhole covers or a few roads and other areas are directly connected to wastewater system. And in downtown areas, people also connected their sump pumps and roof downspouts directly to wastewater system. So this is also creating problems. And also we recommended the installation of flow monitors and CCTVs at wastewater mains to calibrate and validate the current study model using flow monitoring data for multiple dry and wet weather events in future. So periodic inflow infiltration monitoring is also recommended, particularly at deeper network locations where network depth is more than 6 meters, because those locations are getting more inflows from groundwater and from, you can say, sea level rise. And due to age of network, particularly along the coast, pipes are mostly cracked or they have more cracks, and they are getting more inflow and infiltration. So rain barrels can be implemented in areas with high rainfall drive infiltration, because this will restrict rainwater to enter into the sanitary sewer system. And in this way, we can manage these extraneous flows, which are currently creating problems and increasing the cost of operation and maintenance for both collection and treatment systems. Yeah, so this is all from my side. Thank you very much for your attention, and let me know if you have any questions.
Great, thank you so much. I'm checking the chat, and I believe this is all still discussion from the previous presentation. So if I've missed your question for this talk, please let me know and enter any questions you have for the speaker in the chat. Maybe I'll ask one while we wait. When you're looking towards the future, do you have a sense on what is more important, increased rainfall or the continued aging of the infrastructure?
Yeah, it's a good question. Actually, the age is also a big issue. If, for example, in future they will restrict or they will increase the stormwater coverage in the city, then we can stop rain, even extreme events. But the age will allow groundwater inflows to enter into the sanitary sewer system, because sea level is rising, and the age is also a big problem, I think, because we can improve rainwater entering into sanitary sewer system through a lot of with a lot of remedies, but age is also a factor in coastal areas. Yeah.
Great, thank you. Are there any other questions? Oh, here's one. What percentage of Charlottetown
Yeah,
has
actually,
combined sewer?
Actually, currently 0%. The last they separated in 2016 in one of the neighborhoods, and before they managed separate it. But the problem is that the stormwater is still not exist in most of the areas, because when they separated, they didn't install new wastewater networks. So they just combined into wastewater in those areas where there was no a separate system of storm sewers. And that's why the less coverage of stormwater is creating issues. And rainwater is entering into sanitary sewer system.
Great, thanks. Any last questions? Right. Well, it's 35 past. So I think this is a great time to end this session. So I'll just thank all of the speakers we've had today. This was a really very interesting session, and I hope everyone else enjoyed it as well. So
thank you very much, John, Megan, for hosting this session.
Thank you.
right, thanks. I think we can officially end and stop our recording.